Okay, in 7.3, we were looking at that central limit theorem about if you have enough samples, you can approximate a sample mean. Like, what's the probability that the average is a certain amount or less than a certain amount or whatever. Today, we're still going to look at sampling distributions. We're going to look at it from a little bit of a different angle. This time, let's talk about the proportion of a population who have a certain characteristic. This is called the population proportion. And we denote that with a P. Now, in a simple random sample of size n individuals, and X is the number in that sample who have a certain characteristic, the sample proportion is found, and it's denoted with a P with a hat on it, by taking the number in the sample that have that characteristic divided by the total. It's really kind of easy to find. So a computer retailer wants to estimate the proportion of people in her city who own laptop computers. She cannot survey everybody, so she draws a sample of 100 people and surveys them. It turns out that 35 out of the 100 people in the sample own laptops. So the sample proportion is going to be the number who own the laptops divided by the total. And we get 35 out of 100, or 35%, or 0.35. And that's the proportion that own a laptop. Now, the proportion of people in the entire city would be represented by P. Now, we can't interview everybody in the city, so all we can really do is get this sample proportion. But let's say we don't just interview 100 people, but we get a sample here, a sample here, a sample here. Every sample is going to have a different proportion, a different sample proportion. And this is called a sampling distribution, this time of proportions. So instead of finding the mean, we're finding the proportion of the people who have a certain characteristic or think a certain way or whatever. So here's an example of a sampling distribution. So we're tossing a fair coin 5 times. So we have a sample size of 5. Each item in the sample is either a head or a tail. The proportion of times the coin lands on head is what we're seeking, the sample proportion. Now, the probability that it lands heads each time is 0.5. Therefore, the population proportion should be 0.5, right? So here's all 32 possible samples. And so if we don't have a head at all, the proportion that are heads is 0, all the way to all heads, which would be a 1. Now, if we took all of these samples and found the mean of all of these samples, it's going to be 0.5. It's going to be our population proportion. And the standard deviation is 0.2236. Now, we'll figure out, I'll show you how we'll find that. So let's see how that's found. Well, it's easy to see that the mean of our sample proportions is the population proportion, which is wonderful. Mean is the actual population proportion. And the standard deviation is found with this formula. We're going to take our population proportion times 1 minus that population proportion divided by the sample size, and then we'll take the square root of it. That's going to give me the standard deviation. So let's see how we can do that. The soft drink cups at a certain fast food restaurant have tickets attached to them. Customers peel off the tickets to see whether they win a prize. The proportion of tickets that are winners is 0.25. And let's say we have a total of 70 people purchase soft drinks between noon and 1 on a certain day. P hat is going to be the proportion of that sample that win a prize. What would be the mean as standard deviation of all of those sample proportions if we had lots of samples to look at? Well, the mean of my sample proportions is going to be the same as the population proportion, so it's 0.25. Easy. Now, the standard deviation of the proportions is going to be found with this formula. So P was 0.25. 1 minus P, well, that's going to be 0.75, 25%, 75%, divided by the number of people, so divided by 70. So I would take, and you could actually do this all at the same time, square root of, and do it as a fraction, 0.25 times 0.75 divided by 70. And we get 0.051, basically 8. All right, so if we look at this as a histogram for all of these proportions, notice that if we are just doing 5 tosses, we get big, big, big rectangles. But what if instead of 5 tosses, we do 50 tosses? More. We get thinner rectangles and it starts to become denser. It's more of a density curve. And it gets very, very normal. Wonderful. So when the proportion of the population is 0.5, the sampling distribution is somewhat close to normal. When P is close to 0 or close to 1, the large sample size is needed before the distribution is close to normal. So if it's 0.5, it's going to be normal. But let's look at what our common rule of thumb is going to be. It's going to be that the distribution may be approximated with a normal curve whenever N times P and N times 1 minus P are at least 10. Well, this is going to give us our central limit theorem for proportions. So if N times P is greater than or equal to 10, and N times 1 minus P is greater than or equal to 10, then we are approximately normal. The distribution is approximately normal. That means we can use the normal curve. Yay. And our mean of that distribution is going to be equal to the population proportion. And our standard deviation is going to be found with that formula, P times 1 minus P divided by N. Awesome. So a sample of size 20 is drawn from a population with a population proportion of 0.7. Is it appropriate to use the normal distribution, the normal curve? Well, we need to run our test. We need to look at N times P and N times 1 minus P. So the sample size is 20. So 20 times 0.7. So 20 times 0.7. 20 times 0.7 is 14. Well, that's greater than 10. So cool. Now we need to check the opposite. So 20 times 1 minus 0.7, which would be 0.3. So 20 times 0.3 is 6. We cannot use the normal curve. A sample size of 55 is drawn from a population with a population proportion P is 0.8. Can we use the normal curve? So we have to check N times P and N times 1 minus P. So 55 times 0.8 is 44. Definitely bigger than 10. 55 times the opposite. So 1 minus that would be 0.2 is 11. That's bigger than 10. So yes, it meets the conditions. According to a Harris poll, chocolate is the favorite ice cream flavor for 27% of Americans. That means our population proportion P is 0.27, 27%. A sample of 100 Americans is taken. N is 100. What is the probability that the sample proportion of those who prefer chocolate is greater than 0.3? So first we need to check our conditions. We need to check N times P and N times 1 minus P. If this doesn't hold, then we don't have to do anything else. Well, that's going to be easy. That's 27. Then we're going to do 100 times the opposite, which would be 0.73. That's 73. So we meet our conditions. That means my mean of my proportions is going to be equal to the population proportions at 0.27. And the standard deviation is going to be found by taking P times 1 minus P divided by N. Oops, sorry. So that's going to be 0.27 times 0.73 divided by 100. So 0.27 times 0.73 divided by 100 is 0.0444. I'm going to go 4 decimal places. That's pretty good. So now we're trying to find the probability that our sample proportion is greater than 0.30. Well, that's going to be easy now. I have a mean and I have a standard deviation, and I know it's going to be approximately normal. So I'm going to my normal distribution. My mean is 0.27. My standard deviation was 0.0444. And we want to see when we are greater than 0.3. The probability that a randomly selected sample of size 100, more than 30% of the people like chocolate, is 0.2496. Basically 25% chance. Approximately 60% of eligible voters voted in the 2016 election. P equals 0.60. If a sample of 88 voters were polled, would it be unusual if less than half of them voted? Okay, so unusual would mean that the probability is less than 0.05. So first we need to check our conditions. N times P would be 88 times 0.60. Then we have to check N times 1 minus P. Cool, we checked our conditions. Now the mean of our proportions is going to be equal to 0.60. It's equal to the population proportion. The sample the standard deviation of those proportions is going to be the square root of p times 1 minus p divided by the sample size. So square root of 0.6 times 0.4 divided by 88. That's 0.0522. 0.05222. I just went all the way. And we are trying to find out if it's unusual if less than half of them had voted. So we're going to be looking at the probability that our proportion from the sample is less than half, so less than 0.5. So I need to go in and change my mean and standard deviation. .05222. And we want to see what the probability is that less than half of the people voted. And it is 0.0277. Is this an unusual occurrence? Well, unusual is less than 0.5. This is definitely less than 0.05. So yes, this is unusual.